So thank you very much for the opportunity to give this talk. I was not given strict instructions, so it will be a little bit of a random walk what I think is relevant and I mean what we have been doing and where I think we should go after. So I started with this a little bit of context. So why fire, probably for this audience, it just will be a recap, why fire activity has changed. And I really like this slide that I stole from a friend who is an ecologist, and remind us that fire are actually very normal in many ecosystems. They are actually beneficial. So some seeds are only released after burning, and there are plants that have invested in thick protective bark to keep fire out. And also there is this idea of fire as a regeneration of biosystems. But then of course, you know, if fires occurs where should, you have a very fast regeneration. And we all know that fires in many places are clearly outside the normal range. And here is a small collection of what we sometimes call exceptional omega fires. So starting from Australia in the Black Summers and going to Canada last 2 years ago, in fact now, in 2003. And then of course also in Europe at a much smaller scale. But you know, we start to see fires that are burning 350 hectares in one go, like in the Ebro forest near Alexandroupolis in Greece. And then of course at the beginning of the years, the Los Angeles fires, the Palisade fires, they burn just inside the city. So they have a completely different scale of space or rate of spread, but they are all exceptional in their own means, of course, because of the impact they produce either in ecosystem or in terms of human impact. And of course, this 2025 has seen also for Europe a massive hectares. We heard a massive season. We heard before that we hit the 1 million hectares. That maybe is nothing compared to Canada, but I mean, let's not forget that Europe adopt a very strong desuppression policy. So this million hectares means these are all fires that were not stopped immediately. And of course, we have seen the Western Mediterranean being the largest affected, but also massive event for impact, also psychological impact. We had the first mega fires, so fires above 10,000 hectares in UK. And I can tell you, living there, this was perceived like a massive disaster. And I wanted to show this little video from NASA, just to remind ourselves that it's a quite complicated pictures, because while we see these mega fires, I think we are all aware that actually burnt areas going down, which really confuse the public, because the burnt area is actually decrease, is actually driven by the loss of fires in the savanna area because of the change in the land use. And this is really substantial if you see sweeping across, and the total amount is around 23%. This is a decline that has happened just in the last 18 years. So you might wonder why then the total carbon budget from this emission and fire is not going down if you have lost so much of burnt area globally. And this is another problem, because essentially, I will explain what is happening. Just to make a comparison, if you look at the total burnt area also in Europe, which is the red line here from just the MODIS data set, if you consider the role of Europe, not just the Mediterranean, the total burnt area has also declined in the last 20 years. And if you know, Europe has a policy for reforestation because we need to meet the goal of the Paris Agreement and the Green Deal. And the afforestation in Europe is actually quite successful. So we are reaching something like 8% more forest. So you can see that forests are going up and burnt area are going down. But if you look at the landscape flammability, which is, for example, in terms of fire weather index, this is a study that we did just looking at the ERA 5 and if there was a significant trend in the FWI in the last 40 years. And you can say that, I mean, this is well known, of course, the Mediterranean is considered a hot spot for climate change, is warming much faster than the global average. And there is a significant trend also in Central Europe and a not significant trend for the Northern Europe. But I think the global message is that essentially you have afforestation, you have burnt area that is going down because your suppression action are very efficient, but you also have a landscape flammability that is going down. So the question is up to which point your suppression is good enough to keep this whole situation under control. And so why, I was saying before, why we have a decrease in burnt area, but the total emission of carbon from fire seems to be more or less constant. And this has been a puzzle that has keep us busy for a little while, but now I think there is a full understanding that what is happening is that when fires burn, and they are extreme, they tend to burn in fuel-rich area like the Boras forest. So they are much more efficient in terms of extracting CO2 from from number of fires. And this is a study that was published last year in Nature, Earth and Environment, and is from someone in Australia, Cunningham. And it's a very simple study, but very effective in explaining this, because it looks at the top 1% FRP, fire radiative power fires, so the most extreme powerful fires, let's say, in the last 20 years, the one that have emitted the most of the energy. And he looked that there is a significant trend, but only in the boreal forest. So essentially, and the plot here show you essentially the first top 25 globally, and they all happens to be in this region. So essentially what is happening is that the burnt area is going down, but the most extreme fires are going up, and they happen to be in fuel-rich area. And just to add to the picture, things will not go much better in the future. So we did this study to look at how fire weather index that now are seen once every 20 years. So what is the probability that they will be seen more often? And what emerges is that essentially this probability in anything that is green is likely to become double, and anything that is purple or red is tenfold. So it means that any fire weather index that now happens to come once every 20 years, it becomes one every 2 years, 1 other years, more or less. So, I mean, and of course, once again, the Mediterranean come out as an hot spot. So, okay, this summarizes a little bit this context. So, given that clearly what drives fires is changing, this section looks at what are the drivers, what are those fundamental elements that we don't have in today fire weather system. So I think the first things that I wanted to say, and we all know that fire weather index do not try, they have never tried to predict fire activities. They were really tools that try to understand what a fire, if ignited, would look like given the weather condition. So, but so in some sense, they imply that weather was the main element that were driving those fires. And this was a completely obvious assumption for the Bora forest, because fuel was always there. If you have a forest, you have for certain fuel. And the only thing that made the change was, how dry, how windy the conditions were to eventually make fires in those ecosystems become uncontrollable. So I won't explain how we do this analysis for now, but if you take these numbers for real, when we looked at, this is done in the context of a collaborative effort that is called the State of Wildfire Report, where we try to publish one review paper every year to look at the global fire season. And one of the analyses that is conducted there is to take fire events that are of relevance and to try to attribute what drove those events. So here we divide in broad, let's say, categories: weather, fuel, and others, where others is ignition, human influence. And when you look that something pop up, it doesn't mean that the other things are not important. It means that for that time, that region, the explainable model find that cause particularly relevant. It was unusual, and therefore tags that as a main contributor to explaining those events. So if we look at, this is for 2023, of course, there is the big Canada event, there is the event in Greece, and there is heavy burning in Western Amazonia in different periods. And you can see that the weather scores around between 40 and 30%. In the Ebro file, for example, just to make you understand, when you see 60s is others, it means that the weather that led to this fire was not unusual for that season. It was an extremely fire danger, but those conditions were met in many other years before. So there is nothing that can help you attribute, okay, this was so exceptional that it happened because of weather. Weather was very high fire danger, but was not unusual. The week before was exactly the same. And fuel was exactly as in many weeks before. So essentially the model say, okay, I don't know, has to be something that has to do with ignition or something that the model doesn't have, and therefore it cannot justify. So this actually shows you that weather, yes, is important, but in many places of the world is not the main cause. And we will see that this is now accepted, that fuel becomes more and more important because of this hydroclimatic intensification. There has been a lot of paper look at this, at the fact that as the atmosphere warms, if you consider it as a sponge, it can suck up much more water from the soil, so create a broader drought, but it can also release when it's squeezed. In this case, the squeeziness is, the atmospheric circulation, tropical cyclone, things like that. It can squeeze much more water because it can hold much more water. So you will have this, on the two sides of the extreme, you will have extreme condition, both as dry and as wet. And from the perspective of fire, what this means essentially that you will have fuel accumulation, because in wet period the fuel will grow and will grow much more lush. And then during the dry phase, you will have of course, much more fuel to burn, therefore an intensification of the fire. And this fuel accommodation is really relevant in certain region. And of course, in which region is more relevant? In the Mediterranean region, where fuel might be a limiting factors. So, for example, we conducted this analysis for the Palisade fires. This is actually, it was a well-known fact that in California they had 2 seasons before. So the Palisade fires happened here, where you have this dry condition, was in January. So it was very unusual for California to have a fire of that intensity in the winter. And before this period, you had this very wet period. So SPI is these are all anomalies, and this is an indicator for drought. You have a vapor pressure deficit. That is an indication of the transfer of moisture from the atmosphere to the vegetation, and then you have soil moisture and all the various moisture content of the vegetation. And you see that here are all wet. So essentially you create the condition for fuel to be generated, and then you have this that is called like a dramatic rebound, when very fast dry condition, very fast wind just create that perfect situation. And this is something that this is for the Palisade fire, but then you can say, well, this could be a case. So we looked at all the 20 most devastating fire in recent Californian history. And essentially what we found that if we perform the analysis for all, you can almost see the rebound, because most of these most extreme fires happens in the Mediterranean part of California. You also have forest fires in California, in the Northwest Forest Mountains, and they don't seem to have this rebound. And this is because essentially here you have adding fuel to a forest doesn't make that big difference, but adding fuel to a Mediterranean ecosystem that might be fuel limited, it may really trigger that effect. So how do we put all this that we are looking into traditional fire danger metrics and make this switch, in the sense, start to take into account of the fact that the fuel availability might make a difference. The presence, of course, of people, the ignition might make a difference. So to start with, the process that we try to represent is this one, no? So we all know this triangle where weather, ignition, and fuel, the combination of these create this kind of map. This is, for 1 year, fire activity on Earth. Is where fire occurs using, for example, modeling observation, the number of all the fire recorded in a given year. And if we consider the climatology of the fire weather index, you get a map like this. So you of course observe a maximum fire weather index somewhere in the desert. This area would be masked by, fixed land cover max, but this is what the FWI gives you, because so it overly predict. If you want to compare this with this, it's clearly over predicted. If you want to use the FWI for forecasting fire activities. So how do we do? So our idea was just to use AI, of course, to use machine learning, and to say, okay, if we ingest, decompose that triangle into weather, fuel, and source of ignition, and we try to just represent observed fire activity, what we come out with is just something that looks like more the probability of fires. So we constrain our problem. We say, okay, this is what you need to predict fire activity, not landscape vulnerability, fire activity. And we know that what should contribute to these are 3 elements. And so we come up with something that should more or less look like fire activities. And if we do something like this, so we use AI and we put whether we have, we also put ignition and fuel, we come up with a map that looks like this. And this is much more similar to the fire activity, of course, because to start with, the simple hanging fruit is that the fire, the AI learns that here it has never seen a fire. So exclude immediately, desert area. It learns from fire activities as well that, there are always burning in the savanna area and all the rest. So this is clearly a method that is much closer to represent fire activity. And how do we get that? Well, you need to constrain your problem with a lot of data. So we know what is the side of the three sides of the fire triangle. So we essentially mimic the fire weather index, giving the temperature, the humidity, the wind, and the precipitation. Then we add all the information about the fuel, and I will talk a little bit about this. And then you can go as far as you want with the human ignition, because then you can put population, you can put the road density, you can also go all the way to put a socio-economical indicator, things like GDP, your trust in the government, whatever. Because the power, let's say, of AI is that you can really mix all kind of information. You don't have to have a conceptual model for it. It's a statistical analysis that you are performing. But as I say, it's not just about using machine learning, because if you say, okay, I have my fire weather index and I use only these 4 variables, and I make my model understand where this 4 variable works for fire activity, you get a map like this. So you don't go all the way, because your model, knows where fire activity is, but still is confused. Because it doesn't know here, for example, that fuel is not there. So it's not just about using machine learning with the same amount of data that you had before. It's really to have a framework where you add all the information and then you get a map like this. So what is the weight of every source of data? So we conducted some experiment because we were interested as well. We said, so what is really the kind of data that make the difference? And we run our model, and we have a lot of skill scores. And so say that you give 1. So the best skill score is when you use all the source of data. We found that if you use only weather, you decrease your accuracy to 30%. And then if you use fuel only, because in fuel, of course, you have information about the weather, but a very long time scale, because you have the fuel accommodation, you get the best result using one single, let's say, class of data. By any combination of 2 of the categories that we have give you almost 90%. So you're very close to reach the perfect score, let's say. And another interesting things that we did was to say, okay, maybe you reduce the amount of data because I don't have all the data, but I really increase the complexity of my machine learning model, like to say, now you have a very simple one. We use an XGBoost that is a mid-complexity classifier, so you can go to very deep infrastructure. And we found that no, not really. The complexity of the machine learning is sort of taper off, so you can go very in this deep infrastructure that are not really explainable anymore, things that we didn't want to do. And we played a little bit, and we clearly found that having good quality data is the winner here. You really needed to think of what you put inside your machine to have a good result. So I don't have the time to go into details of this, but most of the success, let's say, of the POF, of the probability of fire, stems from having implemented this that we call sparky fuel, that is part of ISNWF effort to put this fire process into its model. So essentially what we have, we really leverage a lot of different satellite information to have a daily estimate of fuel load, both for the very dense part, so of the vegetation, and the light part of the vegetation, and then also fuel moisture content from both the dead part of the vegetation and the live fuel moisture part. And this really needs to be updated in real time. So these are just two maps to show this product. Then I just show this, but I mean, I'm here, so if you are interested in this particular site, I can show you better. Essentially, what happens here is one of the fires in Greece, and if these are two maps from Sentinel before and after, so you see clearly the scar of the vegetation. So since we use in our model leaf area index, so our model knows, you see, the leaf area, the index drops immediately. So our model knows that he has lost vegetation here in this point. So the idea of this model is really to use satellite observation to update the state of the vegetation. So, you know, this is just one point, but of course, when you have burning in massive area, you need this kind of information. So the system now works with data from the weather that comes directly from ISNWF forecasting system. And then we have extra observations that go and inform the sparky fuel model in real time, especially for the vegetation. And these are things like leaf area index and vegetation optical depth at the moment, but we could have many more information now that ESA is launching biomass and all these other missions. And for POF in particular, that runs outside this scheme, use the data from Sparky. We also add socioeconomic indicators that really helps pinpoint where humans are likely to give an ignition. And this is how, I thought to a video, how Sparky look like. So of course you have fire activity here, and you have the probability of a fire. It's clearly broader than when a fire occurs, but the reliability is very good. It means that if in an area you have, I don't know, a certain number of fires, Sparky integrated over an area at that time will give you almost that number. So how does Spark compare to existing forecast? I will just use some of the example to give you a feeling. So this is one day during the Black Summer. This is the FWI. That of course has very high danger in the desert again, but something that struck our interest was this part that the FWI is actually not very high on the coast, and I think this is because the FWI doesn't account for the live fuel moisture content anomaly. Is a representation of the dead fuel moisture, not the drought code and FFMC. So probably this is pushed, and we have done an analysis, and we see that in this region, at least according to Sparky, then maybe Mika can confirm, it was very low, the very high anomaly of live fuel moisture content, also the dead, but this is probably what drove the severity. And you can go up to 10 days forecast, but then when you go to 30 days forecast, since this is trained on reanalysis, you start to really lose skill, but 30 days forecast, I mean. And this is another case that was a very weird event in South Korea this March. And of course, these are a region of where we never really look. But the fire was very bad and it was driven by extreme wind. And we were really surprised how good the POF did, because essentially this is not a region that is usually fire prone. So our events that are a little bit outside the climatology. And one of the best, I think, case we have is this one for Los Angeles, because essentially POF was able, because it has all the information about where population lives, to really fence around Los Angeles during this event. So this, I thought was a very nice forecast. And this is the case of Marseille that we saw before. And we are very pleased that this is being used in something also to check it's not just us. So, yeah, because our new tools, and I understand that it takes time to understand how to use if they are reliable. So, this is all great, but of course nothing is perfect. So this last slide is about what next, what this still cannot do. And I think a little bit is the challenge of predicting the extreme. So as we have said, POF give you an idea of where a fire is going to be, but doesn't tell you if that fire is going to be a mega fire or is going to be an extreme fire or anything like that. It's just really the probability. You might guess that if there is a cluster of probability, it's likely to be more intense, but it's not because it's been trained on detecting the extreme. So one I think of the problem of AI in general is this smoothness, because it's also a problem of any model. Also NWP, I mean, struggles with extreme, because it's calibrated on the mean state. So if you do the same kind of POF for burnt area that you can do, you see that this is the spectrum of the frequency of event for fire size. So essentially, if you are down here, these are events that occurs not very frequent at all. They are very rare, but very big. This is the observed frequency of extreme in burnt area. So it means that massive fires are extremely rare and small fires are very frequent. So the cascading of this is like an energy cascading from the large scale to the small scale, cioè the opposite, from the small scale to the large scale. And just to put things into context, here you are at the Ivro fire, and this is the Alberta fire if it was one single fire, cioè how much was burned in Alberta in 2023, that this was, I think, something in the region of 30 million, maybe hectares, something like that. But the point I want to make, if this is the observed frequency per extreme, your AI model instead predict the yellow line. So while for the small fires doing fine, as he goes into the extreme, the less frequent fire, just also because they are not in the training data set. These events are very rare, therefore it never happens to see them. So you start to predict less and less, and notice that this is a logarithmic scale, so a little difference is a massive, it's an order of magnitude. So it's clear that you lose the capability to predict the extreme. And this can also be seen here when we look at the number of fires that were predicted. So this is the prediction in the Mediterranean for the POF during the summer. So this is the actual number of fires that we predicted during every day of the year, of the years. So the worst burning, according to I think this is from firms. So it was the 13th of August with around 800 hotspot, and then things went quieter on the 31st of August with around 200 hotspot. So what happens here is that the POF over-predicted at around 900 in the calm part of the fires, in the calm part of the fire, but under-predicted in the most intense part of the fire. So it means essentially that this PDF is much smaller compared to the observations. So the observation has a much bigger range. You go from 0 to 800, and we went from 200 to 700. So it means that we cannot see the two extreme of the distribution. And this is the good thing is that if you look at the time in which we made this prediction, we have predictability that reach almost 10 days. So the timing was good, but if you look at the intensity, this was a little bit off. And also, this is just another example where we can't really predict this very unusual fire. So we had one fire in Scotland, and this was not in the record. And this prediction was completely missed by the system because it was not in its training data set, despite, for example, here you have a very clear anomaly of the live fuel moisture content. But the system was not able to relate this with a fire because it was not in its data set. And one thing that I think is important, where we had the discussion already, is that the POF is not equal to extreme fire behavior. POF is just a probability that the fire might be there. And so this is part of a development that we are carrying out, and will probably get to give some indication of extreme fire behavior. And essentially what we are trying to do is to include a fire process inside the IFS. So in this journey, we have, of course, all the variables that we need from the atmosphere, because these come from the model at 9 kilometer resolution. And we have now implemented a 1 kilometer resolution fuel model that is coupled to this atmosphere. And from this, as we say, we can derive metrics like the probability of fire. So what we would like, and I think we are going towards, is to now try to derive a fire spread model, which is not the fire spread model at the super high resolution that you use for your single fire event prediction, but is more a fire model that will be coupled to our atmospheric model, and will burn the vegetation, our nice fuel that we have just created, by looking at single elements of a single starting point, either from the probability of fire or observed from satellite observation. And this framework might give us an idea of which fires is going to spread very fast and therefore being an extreme fires. So we have started playing with MTG, and essentially, yes, this is how our fire spread model might look like. I don't know if you see, some bits are starting to appear. And once again, this is a module that is being using machine learning. I mean, I think this is a very low-hanging fruit, because this is essentially image processing. So it's where machine learning, I think, does really great. And I think this is my last slide. So the idea here is really to have an holistic approach, to take advantage of the fact that the modeling component in the IFS have been developed for years. So you have almost all the variables for the surface. Now we have added the fuel. we would like to start burning our fuel, and therefore having a framework that not only will allow us to help the prevention and also help managing, fire danger, but also start to look at things like the impact that fires have on NWP. So both in terms of fire emission and all the rest, from the surface to the cloud formation and heat release and so on. But this is, there will be time to get there. So just to summarize, I think the most extreme wildfire often a combination of several factors, not just in many parts of the world. Weather is not the only component, it might not be the most relevant component. I think really the forecast, now we have the tools to move from the forecasting of fire weather into maybe attempting to have a better idea where fire can actually occur. And by doing this, I think AI has been great for the ease. I mean, if you do what you're doing, for the ease of implementing different kind of data set into the same framework. And of course, I think I've shown, and I really believe that most of these skills doesn't come from AI itself, but comes from the fact that now we have a lot of data, especially from satellite, and these data really help to constrain the problem and help to extract that difficult information that is fire activity on Earth. And here there is some material if you want to. Okay, thank you.